Based on market research, a company has found that its sales revenue is proportional to its advertising, based on the formula S, for sales revenue, is equal to 20x plus 4xy plus y squared, where x is the amount of money spent on newspaper ads, and y is the amount spent on radio commercials. If the company has $20,000 in its advertising budget, how should this budget be allocated to maximize their sales revenue? So we've got a bit of a constraint here. We've got only $2,000 that we can spend on our advertising, and that is broken down into newspaper ads plus the amount spent on radio commercials. So what we've got here is our constraint, and we should probably rewrite it as the constraint functions we are used to, because we're heading towards constrained optimization, which means we will need Lagrange multipliers and a Lagrange function in just a little bit. So that's our constraint, but what are we trying to maximize or minimize? What are we trying to optimize here? Well, our sales, our sales revenue, which is proportional to, I think it was 20x plus 4xy. Was it just y squared? Let's go back and check. Plus y squared, yes. Okay, so this is our, we might call it objective or target function. The thing we want to optimize. Okay, so we're going to put this together to make a Lagrangian. So we'll have fx, y, and then lambda, our Lagrange multiplier, made up of our target function plus lambda times our constraint function. There we go. So what do? Well, our maximum, or revenue in this case, is going to be found at a critical point of this Lagrangian, and we know how to find critical points. And we take partial derivatives. And the f lambda, that's always whatever your constraint function was. So deriving with respect to x, we'll get 20 plus 4y plus lambda. Deriving with respect to y, we will get 4x plus 2y plus lambda. And to find a critical point, we need to set all of these equal to 0. Okay. Now, looking at these two, if I were to rearrange them, bring the lambda over to the other side of the equal sign, I can see I've got two expressions that are both equal to minus lambda, so those two expressions are equal to each other. If we bring everything over to the same side, we can see that 20 is equal to 4x minus 2y. And I suppose we could divide by 2 on both sides. Okay. So now I've got an expression relating x and y. We also have another expression relating x and y. I suppose we could bring the y back over and we can rearrange it like this. Y is 2x minus 10. And we could take that and plug it in for the y over here. So x plus 2x minus 10 minus 2,000 is equal to 0. So 3x is equal to 2010. Now we have to divide by 3. And maybe you can do that in your head, or maybe we've got to do a little bit of long division. That's okay. We know how to do long division. So x would have to be 670. And then we can either double it and subtract 10, or we can say, all right, x plus what is equal to 2,000. I think that's the easier thing to do. 1330. Okay, so we only have one critical point here. 670, 1330. So, well, critical points are the only places we can have optimization, or we can optimize for subject to a constraint. So this kind of has to be the maximum. So So there we go. So what could we say if we wanted to leave sort of a therefore statement or something like that? $670 should buy newspaper ads. And it looks like you get a bit more bang for your buck with radio commercials. Now, it's always a good idea after a calculation to stop and check, does this kind of make sense? Well, if we think about the equation, we've got a y squared here. Squaring things is so much more powerful than just multiplying them by 20. So we should expect y to be a much bigger number. And yeah, y is almost twice x. So at least this might make sense to us. This should follow. You should spend more on your radio commercials than just your newspaper ads. Okay, but there we go. We've got our final answer: $670 on newspaper and $1330 on radio commercials, and that's how we should spend our advertising budget.